you should know what a regular set is. So again, can someone tell me what a regular set is? Nicole, what's a regular set? When do you say that a set of strings is regular? So Nicole did not answer, so let's move on to Jeremias. Tell me what a regular set is.
When it exists one automaton, that is that set is the language of the
Exactly.
automaton.
Exactly. Very good. Now we're gonna see some closure properties of regular sets. What does it mean, a closure property? Closure properties are very important in computer science and engineering. Basically, it means that you can build from smaller parts a bigger part. Like you see in engineering all the time that. You also see that in computer science when you write programs. So, for example, a typical closure property of program is that if P1 is a program and P2 is another program, P1 followed by P2 is also a program. So you build programs from programs. This is what it's saying. What this is saying is that programs are closed under sequential composition. So you can compose program one after the other, and that give you another program. So this is an example of a closure property of programs, let's say. Just to relate this to other concepts in engineering and computer science. Now we're going to see closure properties of regular sets. Okay. So we're going back here. So remember that you know that if A is a set of strings and B is a set of strings, A union B is this set of strings, and A intersected B is this set of strings, and the complement of A is this set. All the strings that are not in A. Okay. So here is a property. If A is a set, is a regular set, and B is a regular set, then the intersection is a regular set. The intersection of regular sets is also regular. Another property, we're gonna see that later. If A is regular, then the complement of A is also regular. Okay. And the question is, how do you prove this? So I'm gonna try to lead you to the answer, okay? Because this is always what is important. Okay, so the premise is this. A is regular. As Jeremias mentioned, the fact that A is regular, it means that there exists an automaton, let's call it M of A, such that ST, the language of MA is A. This is from the premise. Okay. Let's kind of draw this. So this automaton will have this shape, has of course an initial state, and so on the, let's say, some final states. and some transitions maybe, and so on. This is like a general picture of MA. This is the automaton MA. It has an initial state. One initial state is possibly 0 more non-accepting states, and the final states. So in order to prove this, that is that the negation of the complement of A is regular, we need to build another automaton. Let's call it M of the complement of A, such that we need to show a MA such that the language of MA is the negation of A, complement of A, sorry, is, let's write this way, such that the complement is actually, but the idea is that you can build this automaton from this one. That is an automaton that accepts every string that this one rejects, and rejects every string that this one does not accept. Sorry, accepts. Any ideas on how to do this?
Can we like change the acceptance states? Like what is accepted is now is not, and what is not is now accepted. With the states, I mean.
Yes, very good. Santiago, do you have another idea?
No, I was going to say the same example.
Exactly. So basically what you do is to say, I'm going to change every non-accepting state into a... Look, if there is a string that this one is reading and it gets to this point, it will be rejected because it's not an accepting state. In order to accept it, I just... So what I'm going to do is I'm going to copy this one. Okay, there. Well, that didn't come out good. There. Can you see it actually? So this one is obtained following Johan's idea, like we need to change these states. The non-accepting states become accepting states. And these ones that we're accepting now become normal states. This way, every string that will end up in one of these non-accepting states at the end now will be accepted because this is an accepting state. And every string that before would end up in here and therefore accepted by this one, it will end up here. That means rejected by this one. Therefore, the language of this is the complement of A, which is basically the same as the complement of the language of M of A. It is clear. Any questions?
Yes, I have a question. Why the initial state doesn't get accepted if it wasn't accepted before?
No, I am assuming this is just a picture. If this one, yeah. So if this one was like this, so this one should be like this. Every non-accepting state becomes an accepting state, even the initial state. Very good.
Oh, okay.
Okay, it's
Thanks.
just that I mean, the drawing is just an approximation, but you need to change every non-acceptance state into an acceptance state, and every acceptance state into a non-acceptance state. Juan Fernando, you have a question?
Yeah, teacher, I don't get it. I still don't get it. You change every state from a normal state to a final state? Or...
Yes, every non-acceptance state, acceptance state here becomes an acceptance state here, and every acceptance state here becomes a non-acceptance state here.
Okay.
And what's the idea? The idea is that therefore the transitions are the same. They do not change. So basically when you are reading string, it will be read just the same way. The only difference is when you finished. If in this one you finish in a non-acceptance state, then it will be rejected here. But he will be accepted because it will end up in an acceptance state. Do you understand that? Juan Fernando?
Yeah, teacher. Yeah.
Joan?
What if we have an automaton that only has like one state, that is acceptance? Then the opposite of the regular set will be like, will that still be regular if every state if every string is accepted and we change this to like non-string?
Yes, exactly. So the complement, very good question. So if the language of MA is empty, the complement of this empty set is just the set of all strings, which is regular. They're both regulars. The empty set and the set of all strings are regular. Okay?
Okay.
So basically what I think John was asking was, what if this MA is this one, let's say. This one accepts the language of this one. Actually, this is a good question. The language of this one would be what? Santiago?
Yes, can you please repeat? I had some lag.
Sorry, if MA is this, what's the language of MA?
Wouldn't that be empty?
Mm-hmm. Exactly. Okay, so let's move to a more difficult one, which will lead us to the next situation. Let's suppose that A is regular. A is regular. And B is regular. Then A union B is also regular. So before we prove that a regular language are closed under a complement. Now we're going to prove that they're closed under union. Okay? So again, from the premise, we have this. A is regular and B is regular. So you have M of A. Let's see here. You have M, again, something like this. Something like that, and actually, that was good. So that's your M of A, and M of B will be another automaton. Okay, some transitions. So this is just a picture. It doesn't mean that M of A and M of B are the same or they are different. This is just a picture, okay? This is just to mention that these automata, they have some states. Some of them are initial, some of them are final, some of them are regular, okay? So now we need to build an automaton A union B such that the language of M A union B is equal to A union B. Okay? Any ideas? And the idea is the same. Is you use what you already have, which is an automaton from A and automaton from B, to build this new automaton. Let's see, Santiago has a question, maybe a suggestion. Johan too, and
Yes, but Johan was first.
Sorry, Johan.
Okay. I was thinking like maybe if MA and MB have like some same like some like equal paths, we like we have like a new MC, for example, right? And we put all the same paths that they have in common, and then put like the other branches from those same paths, such that they don't have like anything equal.
Yes, but that's a good idea, although the notion of path is complicated because the number of paths in this automaton might be infinite, because you might have loops, you know. You loop once, that give you a path, you loop twice, that give you another path. So you will have to work out the proper definition of path. You understand, Joan?
Okay.
Santiago?
My suggestion would be to use the same accepting states on the same order, similar to what Johan was explaining on the different path. But if it has the same accepting states on the same order for a particular set of input, we can use that as a union if both both automata have the same sequence.
Yeah, that's an interesting solution, and we're gonna see what the problem could be with your solution, Santiago. And Juan?
No, the same as Santiago says.
Okay, so basically putting the ideas together, the problem with okay, let's try to see the intuition of the solution first. Imagine that you just take this one here. Give me some time to copy this properly. Copy. Okay, there. What I could do is to try to have another initial state here and transition to this one or to this one, non-deterministically. This is basically, I haven't explained what that is, but that would be like a random. So I use this symbol here and this symbol here. And the idea is that you start here and the automaton might choose to go here or to go here. So every string that is accepted by MA could be accepted by this one, because if this one, this will be this one will be this one, right? So this automaton might go this way or this way, accepting either everything that M of A accepts or everything that M of B accepts, which makes it exactly the union of A and B. Now, I cheated here because I'm using these things that they didn't exist before. Now, the solution that Santiago suggested is similar. He said, no, let's basically like glue, melt, if you want, melt these two states together. Just make one single state from both of them. That will be more or less, I'm gonna try to do this. I'm not very good at drawing, so let's see. Like, doing something like this and making this stage as the only one. Now the problem is the following. Suppose that this one has a transition, let's say with an A to this state, and this has a transition with A to this state. Then when you are here, you don't know whether to go either to this state or to this state, because they are labeled with the same. So again, the automaton, we have to choose one or the other. That is, it won't be deterministic. It will be non-deterministic. Therefore, it's the same, in the essence, it's the same as the initial idea I told you. You go this way or you go this way. So it's exactly the same. So Santiago's solution also uses something that we haven't seen so far, which is non-determinism. The good news is that in the next class we're gonna see actually this kind of automata that can choose non-deterministically where to go. And this is not as cheating completely, because we'll show that whatever a non-deterministic automaton can do, there is also a deterministic normal standard automata we have seen so far that can do exactly the same. That is, so we'll define what a non-deterministic automata is. But let's say the theorem will say that for every non-deterministic automaton A, there exists a deterministic automaton B such that the language of B is the same as the language of A. Of course, I haven't quite defined what this is, but the idea is that in a non-deterministic automaton, you could have these kind of things. With A, you go to this state, and with A, you can go to another state. That's the idea of a non-deterministic automaton. This cannot happen in a deterministic automaton because you need to have a function. And this wouldn't be a function because for the same state has two possible next states. Sorry, Johan, do you have a question?
Well, I had one like before with the example of MA and MB, they were using the same sigma.
Yes, they will be using the same sigma. Sorry.
Okay.
That's basically always the assumption, and I did not mention that. Good point. Anyway, so that means that if we have non-deterministic automaton, this problem is easy. And how about this other theorem? There's another one. If A is regular, or if A and B are regular, then A intersected with B is regular. So A and B regular implies A intersected with B is regular. Any ideas on how to do that one?
Teacher, the solution to the last theorem, the union, was the one that Joan proposed, or?
No, more like the one Santiago proposed, but we are not quite done with that yet because we haven't seen non-deterministic finite state automaton.
Okay,
So
okay.
we will see that in the next class. And then Santiago's suggestion will become a solution, but so far it's not, because this is something we don't have yet. But we're going to see another solution. This is just to introduce you to several possibilities. So how about this one? A and B are regular. John?
I mean, my answer to this one is quite similar to the other one, but I was trying to like develop my idea. And what I was trying to say, like, if they have strings, these two sets A and B, they have strings that are the same, they will have the same sigma. Their sigma function will have some like same answers to specific sets and specific states. So we just have to build only that sigma function, like this intersection of the sigma function, and that will be the automaton.
Yeah, that's more or less the idea, and we'll see that in next. More or less the idea. You'll see a nice trick to do that. But this is the constructive way. There isn't, you already have the two theorems that we just saw. Then if you use just the Boole properties of Boolean properties of sets, then you know that if you have union and you have negation, you already have intersection, right? Do you see why this is a consequence of the two previous ones or not?
Can you repeat, please?
So we saw that regular sets were closed under negation and under union, right?
Yeah.
Therefore, they must be closed under intersection. Why? Johan?
I don't know, honestly.
Doesn't this give you an idea? That's the importance of set theory. set theory tells us that this is equivalent to what? The negation of this, right? So using this property, I can prove this theorem. Why? Because you just take the automaton from A and the automaton from B, and then you make the automaton from M of A, and then make the automaton from M of B. And you know that this is possible. Why? Because this is A is regular, so the negation of the complement of A is also regular. So you have this automaton and this automaton. Now, because this is regular, the negation of A and the negation of B is regular, then you can build an automaton from the union. We just saw that in the next one. So from these ones, so from this, you build this. From these two, you build M of the negation of A union the negation of B. Okay? Now, we know that the negation of this is regular and this is regular, the union is regular. So the whole set is regular. So since this set is regular, you can also, from the complement closure of, the first theorem that we saw, we have M of the negation of all that. And this automaton clearly the language of M of the negation of the negation of A union the negation of B is equal to the negation of the negation of union the negation of B, which is equal to A intersection B. Joan?
Yes.
You are asking a question?
Sorry, I left the hand up, sorry.
Okay, sorry, Juan, did you mention something?
Profe, la viñeta es, en este caso, elemento o es negación.
Sometimes you use the same term for both because they are like equivalent, but to be more precise is the complement. It's a set. Okay. So, did you understand this proof or not?
Yes.
Okay, good. Jeremias, did you get it?
Yes, but so we need the union definition, right? So to get the complete.
Exactly. And the union, yeah, exactly. We had this proof, but this proof has the problem that we haven't seen non-deterministic automaton yet. And we haven't proven this thing, right? This is a theorem that we need to prove, and we'll see that in due time. So we're gonna try to do this directly, using something that resembles somehow Johan's suggestion. Okay, so pay attention. So let me see how you look at this. Okay. Let's suppose that you have A and B and they are regular. That means that we have two automata, M1 and M2, such that the language of M1 is A and the language of M2 is B. You understand that, right? So far, so good? Any questions? Yes. Okay. So we're gonna show that A intersected with B is regular, by building an automaton M3 whose language is A intersected with B. So the idea of this automaton is that he would move from one state to another like in parallel, simultaneously, okay? Here's the idea. It's actually quite a nice idea. This is M1 and this is M2. This is an abstraction. This is like a drawing of this. Okay, and as usual, some states will accepting, some of them will be non-accepting. And let's suppose that you have a transition from S to S1 here, which is called A. They have the same as Joan pointed out, they have the same alphabet. So you have an A here, and you go from here to here. And you have an A here. So look at this. This one moves from S to S1 if he reads an A. This one moves from T to T2 if he reads an A. Okay. This one moves from S to S2 if he reads a B. And this one with B moves to T1. Okay. So the idea is to try to make an automaton M3 that moves like simultaneously with A from this initial state to state that represent these two together. So look at this. So M3, since the initial state of this one is S and the initial state of this one is T, the initial state of M3 is labeled like this, is the Cartesian product, this pair, S, T. S, comma, T, okay? And from this initial state with A, you move to S1 to the pair S1, T2. So S1 and T2, because this is with A, it moves here. And with B, it moves to the pair S2, T1. Okay? As you can see, what you're gonna take is the states of this one are labeled with pairs of states of this one. So that means that the state of this one of M3 will be pairs. Okay? So look at the acceptance states of this one. Since this one has an acceptance state that is called S7, and this one has an acceptance state that is called, let's say, T10. So this one will have an acceptance state that is called S7, T10. And in general, if this one has a state P here, let's say, if M1 has state called P here, and M2 has state called Q here, then M3, we have a state called P, comma, Q. So the general idea is very simple, is for every state P of this one and a state Q of this one, you will have a state P, Q. And you will make a transition from into that state in M3 with A only there is a transition with A into P, and a transition with A into Q. Then you have a transition with A into this one. So as a result, it's like you are moving at the same time in both automata. And you will reach an accepting state like this one. Only you will reach an accepting state here, S7, and you will reach the accepting state 10 in this one. So it will be the conjunction. And therefore you get the intersection. That's the intuition. How you define it is like this. So M3, we have some states and some transitions, some initial state, and some final state. Okay. The states of M3 is the Cartesian product of this, the state of M1 and the states of M2. That is the set of pairs such that P is in Q1 and Q is in Q2. Okay, that's what I just explained. Now the final states is the same, it's the Cartesian product of the final state of M1 and the final state of M2. So all the PQs such that P is in F1 and Q is in F2. The intuition is that to be accepting, you have to be accepting in both to get the conjunction. Now, the initial state is the pair S1, S2, where S1 is the initial state of M1 and S2 is the initial state of S2, which is what you just saw here, right? And here comes the most complicated thing, the transition function. How do you define the transition function? That is, we need to define delta of 3. And what if I am in state PQ and I read an A? Where do I move? I need to determine the pair P prime, Q prime. I will move to when I read A in M3. What do you think? How you do it? Any ideas? Santiago?
I'm not sure. I'm thinking about it.
Think of this idea. If I'm here, where do I move with A? To this one, right? S1 and T2. What is S1 here? And what is T2 in this one? So what is this and this? This one is what you get by reading A when you are at S in M1. And this one is the one you go to when you read from T, this A. So, any ideas how you obtain the next one? Johan?
You should like following the same logic that that you used to get to P and Q.
Mm-hmm.
So the next would be like applying the A in the per PQ. Mm-hmm. I don't know how to explain it.
But you are in the right track. That you are on the right track. That's it. Juan, it's exactly as you said. You just need to put it like formally. Santiago?
In that case, just continue with Juan's idea. Should we use instead like delta 1 and delta 2 for PA and QA?
Exactly. This is what you do. Is the pair, the next state will be a pair that you obtain by applying delta 1 to this one. They came up to this one and applying with this and applying delta 2 to this one with A. So and this is a pair, right? The first element is this one and the second element is this one. And here's where you capture the idea of doing it simultaneously. Okay, at the same time it's moving here with A, and at the same time it's moving here with A in the two automata. Is that clear?
Yes.
So this automaton we just built is called the product of M1 and M2. So this is a famous construction, and it's called the product construction. This way you accept the string if and only if that string is accepted in M1 and in M2. And here I did not use non-determinism. So there is an issue with the number of states. What will be the numbers of states of M3? That's a question. How big will be this set? How big is you should know this from my functional programming course.
The product of the other two.
Yeah, so it will be the number of states of Q1 multiplied by the number of states of Q2. So it's going to have many more states, right? It's a product. So let's say it could be quadratic. Okay, so this is the product construction. Any questions? So with this construction, you can prove that if A and B are regular, then A intersected with B is regular. So, any questions? Of course, we have improved the union, right? But now I just proved the union. Why? Santiago?
I have a question regarding the intersection bit, the thing that you just explained, that the different states, it's the combination of M1 and M2, the multiplication. How are we going to be determining which path are we going to take, since it's going to be a big path, a big tree? How are we going to go from one path to the other? Are we going to do it both at the same time?
Yes, because this is, look, in this automaton is still deterministic, right? There is only one state you go to when reading A, and this is this one. Okay.
Okay. So the different states are going to be the combination of this S1 and T2. Always. Yes, there's never going to be two different paths with the same input. For example, A, one going to S1 and one to go into T2.
No, because look, with A you only go here, and with A you only go here. From this pair you will only go here. Okay.
Okay.
So in that way, it's doing it simultaneously. It's like one way to imagine this is like if you move in this one, let's say that Jeremias will be running this one and Santiago will be running this one. So let's suppose that you get the letter A, B. Therefore, sorry, let's suppose my input string says AB. This input string here. So then Jeremias will move here, and Santiago will move here. And then the next, this is A. Now the next one is B. So Jeremias will move here, and Santiago will move here. So after reading AB, Jeremias and Santiago will be, Jeremias will be here in S4, and Santiago will be here in T4. And they are running this at the same time. In this one simulates this because then you will have A here, right? And the product instruction tells me that from S1 and S2 with B, you will move to S4 and T4. Why? Because it's the only one you can go after reading B. So basically, I can simulate what they are both doing by moving in this one. The same number of steps, it's just that it does it with the states here. Do you understand, Santiago? Intuition?
Yes, completely clear.
Okay, good. So this is it. In the class, in today's class, we saw the closure properties of automata. And basically, we proved that regular sets are closed under all the Boolean operations. That means negation, intersection, and of course, the union. Any questions? Okay, if you have no questions, in the next class, we're gonna see this notion of non-deterministic finite state automata, the importance of it, and we're gonna show that they're equivalent to deterministic automata, but they have something to offer. And that thing that they have to offer is simplicity. They are much more simple. They are much, in general, they are smaller in size. They have less states, fewer states, sorry. So this is it. Any questions? Bueno, muchachos, entonces los dejo con Nicolás. En caso que tengan más preguntas acerca de las tareas o algo que quieran aclarar con él. Entonces, allí los dejo. Nos vemos el viernes. Que estén muy bien.
Muchísimas gracias.
Listo, profe,
Listo,
muchas gracias.
Muchas gracias, profe. que
Nos
esté bien.
vemos.
Gracias, profe, que estés bien.
Bueno, muchachos, no se vayan todavía, por favor. Ya me fueron la mitad.
Nicolás, una pregunta, ¿para cuánto quedó la monitoría
Decime.
la final?
Eso es lo que quiero hablar, weón, porque es que esta gente no contesta las encuestas.
Pero,
revisamos eso.
¿cuántas personas le han contestado?
¿Ves?
Vení,
Está
miremos
grabando
eso.
la clase.
Que se grabe, no importa.
Ah, bueno, pues.
Es más, hasta mejor que quede grabado. Ahí se ve mi pantalla, ¿cierto? Sí.
Sí, ahí se ve.
Entonces, la han respondido 2, 4, 6, 8, 10, 12 menos 1, 11. ¿Por qué menos 1? Porque acá se respondió 2 veces. Y la que mayor votación tuvo fue ¿esto qué es? El lunes de 4 a 5. ¿Sí o qué? Según esto. Ah, miento. El miércoles de 2 a 3 tuvo 10 votos. O sea, ¿le sirve a todos menos a una persona? A 2 personas. A Joan y a Sebastián.
Me cogieron
El
con
siguiente
física en
es...
esa hora.
Ok, de 2 a 4, supongo.
Sí, 2 a 4 física.
Y aquí el lunes de 4 a 5, María y Sebastián y Nicolai y
No,
Flori.
la verdad no tengo problema tampoco, la hora que lo pienso. Para el
¿Quién
lunes.
está hablando? Ah, María,
María
listo.
José.
¿Y Sebastián?
Sino que yo puse, yo pensé que era que uno ponía pues el día que uno quisiera, pues proponer. Y me faltó llenar los otros horarios. Pero ese día sí puedo.
¿Sí?
El lunes yo tengo clases de 2 a 5.
Ush, ¿de quién?
Ah, no, de la opción complementaria.
¿Y Nicole? Molineros. Ah, verdad que no puede hablar. Perdón. Molineros. Ah, bueno.
Ve, y si pones una el miércoles
Mm.
de 2 a 3 y la otra el lunes, 1 hora y 1 hora.
Ve, ahí Nicole dijo que sí podía
Pues,
el lunes a esa hora.
pues se tendrían que ver los mismos temas, 2 horas diferentes. No sé, siento yo que es como perder un poquito el tiempo. Venga, les muestro mi horario y ahí escogemos más fácil. Con mi horario. Quería llegar a eso, pero bueno. Ah, listo. Después de las... Ah, bueno, no, yo puse hasta las 5 nomás, creo. Hasta las 5, sí. Después de las 5 yo puedo lunes, martes y miércoles. Ya ustedes dirán.
Con que el
Ve,
miércoles
y
no
si la
sea de 4 a
hacemos
6
el
está
día,
bien.
¿Cómo?
Para mí, si el miércoles no es de 4 a 6 está bien. O sea, puede ser en cualquier horario menos de 4 a 6.
y si se hace la el miércoles y se deja grabada porque no puedo asistir.
Pues normalmente lo que se hace es que siempre queda grabado y se sube a YouTube en la lista de reproducción que les mandé por acá. En links, ¿cierto? Pues... Ah, bueno, y yo las grabaciones de las monitoreas las quito antes del parcial. ¿Por qué? Pues porque normalmente se hacen ejercicios que muy probablemente salen en parciales.
Entonces, que descarguemos los videos, dices.
Si ustedes quieren, pues marica, los parciales son presenciales.
Puedo
Pues
llamar
para que los
capturas de
quitas,
pantalla de
como
la
podemos ver videos
monitoría.
en clase.
Pues... Eso lo va a preguntar. De momento no les prometo nada. El lunes de 5 a 6 les sirve. De 5 a 6.
El lunes de 5 a 6 está bien.
Me
¿Hay,
sirve.
¿Hay alguien a quien no le sirva?
¿Dijiste lunes?
Lunes de 5 a 6.
No, perfecto.
Bueno, el que calla otorga. Y el que no viene, pues más. Pues... ¿A Nicolé le sirve el lunes de 5 a 6? Es que no puedo hablar, pero puedo escribir. Asumiré que sí. Pues muchachos, sí. Si a todos les sirve, entonces pues el lunes de 5 a 6. Y si ustedes quieren 2 horas, pues de 5 a 7. Yo no tengo problema. Que va a ser un poquito aburrido, sí, pero no. ¿Qué hacer?
Todo sea por pasar la materia.
Hombre, no diga eso. Diga eso que después. Espérate que se está grabando.